in this prototype, we're going to assume that we have a complete modeling of a board, and we want to model a random firing strategy. Even though we may not have the complete modeling of the random strategy we're playing out the board, I think we can assert that we would be able to do that just given enough hands-on keyboard time, just a couple more minutes of time, and with just a little bit of checking to make sure we don't have some transposition where we thought the horizontal was the vertical and the vertical was the horizontal, the width is the height, and the height is the width. But beyond that, I think that the uncertainty and the fear of not being able to deliver something within a fixed variance of time, saying, I can deliver the rest of this with 1 more hour of time, I think that has been eliminated. So what we'll do is we'll actually hard code the board, and we'll look at the firing strategy. And as part of this, one thing that's going to be helpful as I go is I want to do a little bit of visualization of this as I go. So I have just a couple of set up color codes, a couple of ANSI escape codes, just to allow me to do things like redraw on the screen and also change the color of things. Here, I'm going to go back to my implementation of the board and my implementation of the individual piece. And here, I guess the piece is a name tuple. So the piece is some kind of name tuple with the name of the piece and the size of the piece. And the ships are each of the pieces that I have. So here I'm just going to model, say, the battleship and the destroyer. I think that's relatively representative of the game I want to play. And I'll hard code my from random with some random positions because I think, as long as I am able to find the time to get back to and complete that, I'm pretty sure that I can complete that without too much difficulty. So this is going to be my starting point. And here you can see, these are the ships that we have, and that's a dictionary, and then we have our post init. And in our post init, it's largely what we had prior. It's just generating the layout given the ships, and then our from random is basically taking something. It's going to take a couple parameters that it's not going to use for now, but that'll allow us to illustrate, areas in the API where we need to perhaps complete this effort. So here, that's ships, and the ships, all the ships that you're going to place, or the pieces that you're going to place, should just be determined from all the ships that you can possibly place. So there we go. And here we'll have a little bit of starter code just to make sure that we can get the rest of this working. And so here we have a board constructed from some random placement, and we have to think about the random firing strategy. Well, the random firing strategy probably initially doesn't need a lot of information. This is a very simple implementation of a generator. What you can think is a random firing strategy is an agent. And anytime we have an agent model, an object-oriented approach is one way to implement it, or a coroutine is another very simple API for implementing some kind of agent model, as long as we're able to trace out what the inputs and the outputs are for that agent, what the agent needs to know, and what the agent can tell you. And so very likely this is just an agent model with a coroutine standing in for the strategy. When I say when you need to figure out the entities for the thing you're designing, not all of those entities are going to be physical entities. The board is a physical entity made of plastic. The pieces are physical entities made out of plastic. Firing the shots, the little pins, those are physical entities made out of plastic, but they may not really exist in any direct form in my code. The strategy is not a physical entity, but it's a conceptual entity dictated by what I want to be able to do with this code, namely that I want to be able to implement many different strategies and have these different agent models play against each other and try and see, given a particular strategy for placement, how does a particular strategy for targeting happen to work? Or is there some playground that I can use in order to identify which strategies are more effective in the aggregate? So it's basically a battleship simulator. And so probably what I want to have here is I want to have some code that looks like this. I'm going to create a random fire strategy, and I'm going to say for each shot in the random fire strategy, I can have the shot land on the board, or I can have the shot, I think we had a nice term for it before, we can have it strike the board. And this is going to have to give us some information. And it's going to have to give us some information about what the result is. And then based on this result, we're going to have to determine what we want to do next, like whether we want to print something or whether we want to terminate the game. Now, clearly, I also need to say if my active ships, okay, if I have no active ships, then I can terminate this. So I might do something like this, and you can see this is the general structure. I'm going through every shot of my random strategy. I am determining whether there are active ships on the board. If there aren't, stop. And you can think here, this is probably one way I could do this, but maybe a better way to do this would be like this. I might actually make this more explicit as a while loop that loops while you have any ships that are active and then gets what the next shot would be of the strategy. So I might have something like this, shot equals next from the strategy. Or, again, I think this makes a lot of sense because what I can do is I can send back into it the previous result. And so here I can say my first result is always none because nothing's happened yet. And so this gives me a little bit of an insight into, the very first shot is always a shot in the dark. Okay, for this I know exactly what I need to implement. So on the board, I need to have some way to implement, or I need to have implemented what ships are active. And that's pretty straightforward. But one thing that I am missing here is that I don't have the state of the game. So I might actually also need to model the state of the game. And I guess the state of the game might be each ship and how many of the squares of that ship were hit. Because then what I can do is I can say, or how many of the squares are alive. That actually might be a little bit easier. So I might do something like this, ship for ship in ships, because that should be keyed on those. And then here, I'll model this to, each position. It's a very simplistic modeling. And then here I might say, you can think this is actually even a counter object, but we'll keep it simple for now. Here I might say this is ship for ship in ships in self.ships. If and this is the hit points for the ship, or this is the destroyed sections. So this is the hits. If the hits are less than the ship's size. And one thing that you can see here is I could have written that as a generator expression, but there's a very small size of things that I'm almost certainly going to materialize it immediately, so it doesn't really matter. Here you can see one of the things is this active ships. I could have just returned a true or a false value, but the reason I like to return this structure is somebody might want to print out what the ships that are still active, at least according to what they know, because the other player does sort of have a sense of what the ships are active, or the overarching architecture code might want to be able to say, oh, these are the ships that are still in play. For my random fire strategy, this is going to be a coroutine that more or less runs forever. And I think this is one case where the random fire strategy shows us one parameter that we didn't really use that we need to actually make use of, namely the board size. So I'm going to pass in this board size here, even though it doesn't do anything yet, just so that I can make sure that it's pretty clear that any one of these strategies needs to know the board size. Here's one unfortunate thing, though. The random fire is based off of this one parameter. Why the board size? Why not some other configuration parameter that's passed to the board? And I'm passing around this thing, and it's really just a tuple. It's really a value. It's a constituent part of the board. Why do that instead of giving it the initial state of the board itself? That's a little bit unfair because you can imagine that if the random strategies are written by untrustworthy coders, they have access to a little bit more information than they should, like the layout. And so, you could make your random strategy a lot smarter than it is. But what you would then have to do is you just have to tease apart the live state, or at least the board shape and the board parameters separately. So what you do is you just kind of tease this apart and do like something like board params and then kind of sequester some of that data in one place. For now, I think minimizing the total number of entities and retaining my flexibility, because there may be some other information that I need to pass here, like that might be relevant for me to use here, and I just don't want to pass values around. So here we have something that looks like that, and this is going to, okay, let's see, we got this going. And by the way, we need to actually return this thing just to make this work. And here, I think we can at least hard code the locations of two pieces. So I think that gets us moving pretty quickly. So here we go. Let's put this in the upper corner, and let's put another piece in a lower corner. And so we'll put the destroyer, I believe that's the other piece we have. And this is pretty small, so we'll put this at 9, 9, or 9, 8, and 9, 9. And I guess these positions don't really have an ordering associated with them, so they're going to be, this is going to be a set instead of a list. So there we go. And this should be ship for ship, ships.items. Very good. And this should be self.ships. Perfect. Oh, not quite perfect just yet. And this needs to be each one of our pieces. And so here we need this to be ship.value.size. Yeah, and that's one unfortunate thing here. You know, we probably have to feed that in here. We'd probably do something like, you know, property def size self. Return self.value.size. Pass in a couple of these things just to make our life easier. So we might do something like that. So for one of these enumerated types, we can kind of eliminate that. Now the last piece is this should be a ship.size is a set. So let's figure out why that is. And this should be self.state, not self.ships. So you can see we gotta just make sure we have things working. Fantastic. Now, the next error is I just haven't implemented this strike, and this strike is pretty much the response to some hit being passed to us, and this returns some result. So I think there we have some working code. Now, and I think we even have I think we can do the random positioning of the board. So let's actually, or the random strategy. So let's get a random number generator, seed it, and I believe, because I'm thinking ahead just a little bit, that all we need to do for a random strategy is identify what the targets are going to be, and that's just going to be the Cartesian product of the board size. So the boards, and so here what we also need to do is we need to actually keep track of the board size. So here we go. And using keyword arguments here gives me a little bit of flexibility. It's a little bit more pain, but it gives me a little bit of flexibility in case I choose to move those things around. So now that we have that, we can actually ask the board for its size. And here we can do, this would be the Cartesian product of that range and that range. And if this is assuming that it's two-dimensional, obviously, if we have, you know, a multi-dimensional, three-dimensional game of Battleship, then we have something else going on here. So there we get the targets, and then we're basically just going to shuffle these targets and pop off of them. So here we can say while targets yield targets.pop. Very simple random strategy. Doesn't take any additional information in, and you can see that obviously since the game doesn't terminate, you know, this thing runs to completion and then tells us there's nothing more to do. So you'll see this thing actually works, and it's going to shoot at every position and then run out of places to go. And so here, you know, whether or not the strategy succeeds or fails, I guess if this thing hits a stop iteration, we have to do something with it. But that's a little bit artificial because we should have hit all the positions on the board before that happens. So let us then implement the striking, because I think that gives us the last piece that we really need to prove this all works. So for the striking, here we know the layout, and just to make my life easier, I'll just do one hit and then take a look. So we know the layout. We know where you tried to strike, which was that position. And so we can basically say if the hit's in the layout, then you know you return hit. Otherwise, you return miss. And we can at least print out this result. So that's a miss. Let's just see a couple of these, and you can see there's a couple of hits in there. There should be one for each position before this thing terminates. And so now we just need to also update the state of this. So if we hit, then we might say self.layout of this hit. This is the ship that we hit. And here we turn this back up. And one little trick that we can do is we can always do this from sys import exit, or something that I actually really like doing, especially if I'm using an IDE that has this. I'll say from sys import exit, import sys. I'll set the breakpoint hook to exit so that I can put breakpoints in this code and they just terminate execution. So I can do a little bit more print debugging. You can see that's the first time it hit something. That was the ship. And then that means that I can do self.state for that ship plus equals 1. So that indicates that that thing is there. Obviously, I should probably take into account whether this thing has been hit before, but that's a small detail I haven't really taken into account. Really, this should probably be a set of all of the locations that have been hit. That way, I don't even have to worry about that. And then I just have to do something here in hits. I'd have to just make sure this is the length of this thing is less than or equal to the size. So that at least eliminates one consideration for me. And I think that's really all I have to do in order to make this work. Let's see. So here I hit the ship. I set the state to add that in there. Let's take a look at the active ships afterwards. And we'll see if we can assess whether this prototype is ready to go. Take out our breakpoint. And you can see the destroyer was never hit. So we got to figure out why that is. So here we keep missing. And you know why? Because we put it off the board. The board starts indexing at 0. So got to be a little bit careful when we hard code some of these things that we don't accidentally create these anomalies that are, otherwise would be pretty tricky to deal with. Now, obviously, I need to be able to, at this level, figure out what was hit and to print that out. So I need to return something better than hit. Maybe what I do is I return a result. And I'll show you one more thing. You can think that here, based on the result, we want to do one or two things. So if it's a miss, we want to say something like, you missed. If it's a hit, we want to say, you hit, and you hit this thing. If it was a hit and a sink, we want to say, oh, you hit this thing, and you sunk this thing. Well, here, what you can think is I'm trying to do some sort of dispatching based off of some notion of what kind of thing I got, based off of a notion of what type of thing I got. This may be a case where it might be very, very fluent for me to actually just use isInstance. So I could say something like isInstance miss, and then here I say you missed. Or if this thing is a hit, I say you hit. And I can even say you hit the result.ship. And I should do it like that. And actually, you should do it like this even. And I could say, and if this thing is instance, a sinking, then you can say you sunk the whatever. And this is where we put exclamation points. And so in order to do that, this is actually fairly straightforward. I just need 3 classes that represent this result. And I just need to have just a little bit of at least initially object orientation, at least initially inheritance, although I can always mock these things up with a meta class and an instance check. But the simplest way for me to do this would be just to have a frozen data class. And this to be a miss. And the miss doesn't really have any fields associated with it, or even a name tuple. And here I have a hit, and this has what ship it hit. And this is one of those things. And a sink, or a sinking. And here, this is just a type of hit. And so there, what I can do is I can say, okay, this thing should be a hit with the ship, and this thing should be a miss. And so you can see, there we go. And then finally, I can say that if self.state of the ships, the length of this thing, is equal to the ship's size, then it was a miss. Sorry, it was a sinking. So I can do something like this. There we go. So we have a fully working game of Battleship with a random strategy. You can see we first sunk the battleship, then we sunk the destroyer. and everything seems to be working. We're on the right track. And there are some missing parts that we haven't really implemented. We really should be checking, we really should be randomly generating this, but I think we've proven what we're able to do.